Chat Physics, my name's Joe Rowing. You don't need loads of resources in order to teach radioactivity. There's lots of brilliant things that you can draw on, and in fact radioactivity itself is inherently fantastic because you're talking about transmutation, things spontaneously turning from one thing into something else. I've written a big blog post, there's the link there in front of you. Go and have a look at that and talk to me about it. I'm very happy to talk to you at great length about all of this sorts of stuff. If you are going to use sources in schools, please make sure you get it right. Talk to the experts, people like CLEEPS and your radiation protection officer in your school. They'll help you with the fine detail of it. So radioactivity started really with a great story, which was a failed experiment by Henry Becquerel. He was looking to see if sunlight was absorbed by rocks and re-radiated as kind of nuclear radiation. The short version is it was cloudy, it didn't work, but the photographic plate developed like this anyway, and so that property, that radiation, must have been intrinsic to it. Radiation is full of misconceptions. One of them is that it's all green, everything is green if it's radioactive. That's not true, and it stems essentially from this. The radium girls are a really tragic story, really great depth of information there to talk about ethics and to talk about health and the effects of radioactive materials and all sorts. They painted watch dials with this radioactive paint that glowed green, so there's our misconception, there's our kind of the root of it. In doing so, they would lick the brushes or use their mouths to shape the points of the brushes, thereby ingesting some of that material, and they suffered enormously as a result. Do look at it, it's a fantastic story, really engaging. Probably the biggest misconception is the irradiation contamination one. This headline is a great example of that misconception. Radiation, so the stuff given out from the nucleus, didn't travel from Chernobyl to the United Kingdom. Alpha particles have got a very, very short range, a few centimetres, because they're very ionising. Beta particles have got a longer range because they're a bit less ionising. And whilst gamma, which is part of the electromagnetic spectrum, could get from the Ukraine to the United Kingdom, there is so much earth in the way that it would probably all be absorbed. So what was it actually? The explosion was mostly a conventional explosion which scattered radioactive material up into the atmosphere, which drifted across Europe, falling on different countries, for example Wales, where even to this day there is a higher than normal background in some areas. So contamination is a really big problem because you're irradiated continuously. One-off irradiation, much less so, and in fact we use that to do things like sterilising surgical instruments in order to make them safe. It's really important, and I'm going to spend just a bit of time talking about things like Radithor. Okay, so this was marketed as a panacea, a great cure-all. You know, this, if you had a backache, this would solve it. If you had a headache, this would solve it, and so on. In actual fact, this is poisonous. People were ingesting radium and suffering radiation poison as a result. And so the purpose of education around these things is to stop this from happening, and it still is. You can still buy a wristband which claims to give off powerful negative ions. It's got ion producing materials in it, so it must be radioactive. Or you can pay to go and stay in a mine where you're inhaling radon gas. Now, radon gas is an alpha emitter, which isn't so big a problem outside the body because our skin is able to absorb most of it, and in fact the bit of the skin that does the most of that absorbing is dead. But if you inhale radon gas, then you've got this alpha emitter right next to living tissue, and so any ionisation that happens is likely to disrupt living tissue, is likely to ionise DNA, for example, and that causes it to replicate badly or not at all, and can lead to cancers and all sorts of horrible nasties. So it's really important that we educate around this area well so that people can be safe. So where radioactivity comes from is essentially the tension between two different forces, and we don't even look at one of those until A level. So here's the structure of the atom. There's protons in there, positively charged, repelling very strongly but somehow stuck together. The bit that you only really meet at A level is the fact that they're stuck together by this thing we call the strong force. And so the interplay between the strong force attraction and the electrostatic repulsion is everything really when it comes to nuclear stability. And you'll see that as you add protons on the x-axis here, and you add neutrons, or protons and neutrons, so the total numbers on the y-axis there, you've got a particular bit where you have stability, and if you stray too far from that, you have a nucleus which is unstable and therefore is radioactive and likely to give off either alpha or beta emission and move back towards that line of stability. Pretty well all you need for GCSE is here. Something like uranium, for example, decays to thorium by giving out an alpha particle. Alpha is 2 protons, 2 neutrons, very highly ionizing because it's got a positive charge of relative positive charge of 2. It's got a very short range because it interacts so strongly. The PHET simulation on this is really, really good. Do have a look at that website. It's absolutely fab. I really recommend it. Beta, likewise, beta is the other particulate emission from the nucleus, and so this is an electron usually. Sometimes it's the antimatter equivalent of an electron, so a positron, being emitted, and this is it for the nuclear kind of emissions. There is a little bit more, particularly when you get to A level. You'll need to see that there's neutrinos involved in beta decay as well. But then also there's gamma, and gamma is essentially electromagnetic radiation. So if you like, it's energy which is left over when you've got something like an alpha decay or a beta decay. Some of that nuclear store becomes kinetic, and some of it will go to electric magnetic in the gamma. The classic way to talk about the differentiating between these is the absorption experiment, where you have a GM tube, and our GM tube is really simple. It detects radioactivity by an ionization event causing a little spark inside it, and the counter counts the sparks. And so you traditionally put your source in front of this and you count the number of sparks, and then you put different materials in between in order to demonstrate how different radioactivity emissions are absorbed. And so you can do that with this. Now, the original company doesn't appear to be running anymore. The visual simulation.co.uk doesn't seem to be there, but the bit of software is still available at radiationlab.software.informa.com. I think this is really, really good, but it's unsupported, so use at your own risk, I guess. But this is a really nice recreation of the classic experiment. VP Lab is also really, really good. If you can get in on one of their training events, then you can get this fantastic thing for free. I really recommend it. It's got some great radioactivity sims. All of the kind of classic demos that you might want to do in the classroom, you can do through these 2 simulations. So when talking about this stuff, you can also use other things around and about. So people are naturally radioactive. Radioactivity is a natural part of our environment, of our world. The Earth itself is naturally radioactive, and you can see from this map that down where I am in the southwest is particularly radioactive compared with elsewhere. One of my favourite improvised sources is simply a balloon. If you charge a balloon and you hang it up in a room, some of the ions, which are daughter products of this background radiation, so some of those are radioactive ions, they will be attracted to that balloon. They'll stick to the surface of it. So if you carefully deflate it and put it in front of a GM tube, you'll get a very significant count. And you can even do the classic demo of putting a bit of paper between your balloon and the GM tube and show that most of the emissions are alpha, which actually you'll see there's a table here telling you what those isotopes most likely are. And you can see most of them give off alpha. So you can do that experiment. That source, that balloon, is perfectly safe to just dispose of because you're just using background radiation. Other improvised sources are not so good. So this rock here is pitch blende. Please don't use this stuff. You can pick it up off the beach, but the trouble is it is a rock, and so it's likely to be very dusty. It's likely to contaminate stuff. So that's a no. Thoriated welding rods, on the other hand, are relatively safe to use. They're a weak alpha emitter, and you can use those in cloud chambers and all sorts of things very safely indeed. Again, consult CLEEPS, talk to your RPO. Brazil nuts, believe it or not, can be quite a good source, but you need the Brazil nuts from Brazil because where the Brazil trees grow in Brazil happens to be a bit like the southwest here. There are a lot of radioactive isotopes of potassium, and so they are accumulated by the tree. So there's a bit of bioaccumulation going on there, and that radioactive isotope is concentrated in the nuts. If you buy Brazil nuts not from Brazil, they're not anything like so radioactive because there aren't, where they grow, so many naturally occurring radioisotopes. That in itself is a really nice demonstration. 2 bowls of Brazil nuts, one quite radioactive and one not at all. Half-life is a fantastic thing. You don't need radioactive materials to demonstrate half-life. In fact, you can do it with tubes of water and how quickly they drain. You can do it with the froth on beer. So after, I think it's 4 minutes for a typical beer, the column of froth will have halved. Another 4 minutes later, it will have halved again. You can do it with cake in the staff room, or I've done it with the tub of heroes like this on top of a data logging set of scales. Put it in the staff room and you'll see that the mass of them, i.e. the amount of heroes that you've got, will decrease very quickly as everybody rushes in and stuffs their face full of chocolate, and then that will tail off in a classic exponential curve. You can extend this to things like carbon dating. So this bottle here constantly empties, and I'm filling it up with water constantly, and that represents a living tree taking in carbon-14 and that carbon-14 slowly decaying. As soon as I stop pouring it in, i.e. the tree dies, the level of carbon-14 drops, and it will do so exponentially. If you want to go for the classic dice rolling type simulation, you can do. I recommend actually that you use Lego like this, and that when you roll it, a decay is when those bricks land stud side up, and then you stack those bricks up, put them on the table, roll all of the rest of them, repeat that, and it will automatically create an exponential decay curve. If you've got more able students, if you've got particularly A-level students, there's a link there to an article that will allow your students to test the dice rolling model and see if it is in fact a valid model to use. That is a research paper that your students can genuinely test in the scientific fashion. A brilliant activity, have a go. And so hopefully that gives you a quick flavour of some of the sorts of things that you can do with very little about radioactivity. If you want to know more, Talk Physics is fantastic, have a look there. Science Spark, the IOP, is brilliant, have a look there. If you need some more detail about the specifics about what's happening in beta decay or alpha decay, for example, recently Christina has done a brilliant video. Do have a look at that. It's freely available. It's through Physics Fuel, and there's loads of stuff through Chat Physics as well. Also, please do get in touch with me. Thank you very much indeed. Check out the blog post, and hopefully I'll see you around. Bye.